Thank you for this very generous presentation. And yeah, so like Mike said, I think one of the key things of this presentation I will give today is a little bit of discussions that I had with Adrian Hammond, who's here. I can see him, say hi. And I think also the motivation for this a little bit, I want to say this, is how arbitrary the concept of age as a chronological age as we use it is. And sometimes we take this really for granted because we're so connected to age. Age is such an important variable in demography. And we sometimes forget to take a little bit of step back and how could we relate the indicators we have in an age, sort of like an ageless perspective. So kind of like question the age as a chronological age as a concept in itself. So this is a little bit some of the spoiler alert of the implications of what we're doing, so you keep this in mind. And I'll also excuse a little bit that this is a bit of a somewhat technical talk, but I'll try to make it less boring. And I will also have to, unfortunately, go a little bit back and forth into presentation slides because we had a little bit of a technical problem rendering one of the figures. So I'll start with one of the presentations, but then I'll switch just to show one figure. We presented this work. I presented this work together with Adriana at the mathematical demography session at PAA. So that's some of the slides will be from there, and the others are the ones that I didn't really know. So I'm sorry for that, but it's just to show you a couple of figures that unfortunately didn't work for the first time. So now I just share this thing? No. Okay.
It's open.
Mm-hmm.
Just on Adobe, I think.
Yeah. Yes. Okay. So yeah, I'll start with this one. Also because it's got our name here. Yeah.
So you can go to the full screen.
There. Yeah. So yeah. So again, the title of the work is "Cheating Death: Beating the Odds to Longer Survival," and I explain a little bit of why we're meaning by that. And with it, I'll put examples of. Thank you very much. About two important examples of lifespan, of extremely longevous lifespans. And that is an example of a human species, Jeanne Calment, and cream puff, which is the most longevous cat which we have data for. And the common thing between these two is that they continuously cheated death. Beats the odds of dying many times when we consider the average mortality experience that was expected by their cohort of birth. So Jeanne Calment was born in 1875 and died in 1997. And her lifespan has been recorded as 122 years, 0.4. According to the Human Mortality Database, the cohort, the life expectancy at birth for her birth cohort, so the individuals that shared her birth year, was around 48.59. But she lived much more than that. And what we know about Cream Puff, he was born in 1967, died in 2005, and his lifespan was 38. And the life expectancy at birth born this year was 40. So, and then we started thinking about the myths that exist around cats, and we do know that as all cats, Cream Puff has lived 9 lives. But of course, there's a debate on culture. Some say it's 7, so it's like
Exactly.
so either 7 or 9. But we don't have this data for Calment. And a little bit of the provocative that we were thinking was, how could we maybe conceptualize extreme longevous lifespans in a different perspective, not only considering the total lifespans and life expectancy, but in terms of lives lived. And I will show how this is relevant, and it's not only a curious exercise, but can be important for us to understand longevity in a different way. So, and this idea is not I mean, we're putting a creative spin to it, but there's the way that that longevity is sometimes expressed in like older papers in demography, for example, from Gombert's, is that one could understand longevity as the average exhaustions of a man's power to avoid death, or the portion of his remaining power to oppose destruction. So it's a little bit of this idea of thinking about not only the time that you have lived, but thinking that living requires a lot of effort in the sense of you can conceptualize longevity as a consistent and continuous effort that individuals have to make in order to avoid death. And the research agenda surrounding longevity has focused a little bit on broadly on three aspects. So trying to understand trends and patterns in longevous patterns of lifespans. Also, there has been a lot of literature on advancement of methods to maximum lifespan in the form of the mortality hazard at extreme ages. And of course, a lot of effort in trying to validate centenarians and supercentenarian, like the effort of the International Database of Longevity. So the research agenda has broadly focused on these three perspectives to try and understand longevity. So trends and patterns, advancing methods at the maximum lifespan, and validating centenarians and supercentenarians that we have knowledge of, like Jeanne Calment. But our direction of research takes a little bit of a different route, and we ask the question in a different way. So our question is, how many times does somebody need to cheat death in order to reach a specific target age and beat the odds of dying, given the average mortality experience of their cohort? So in other words, how many times does someone need to beat the odds of successively outliving his or her expectable, so to speak, age at death, in order to reach a target age, a given target age? Now, this is a little bit in line with the theory of aging of Strehler and Wisdom, which I'll discuss a little bit in conclusions, where in order to reach older ages, one's intrinsic vitality must surpass the extrinsic challenges to survival. And we are referring to this individual process as cheating death. So cheating death is this individual perspective. It resembles a little bit the approach by Vaupel and Yashin of recruited resuscitations and life-saving from Wittgenstein. But we're not comparing here mortality scenarios. We're really trying to look at the individual and the cohort perspective. And then, of course, we had to then go to the mathematics of cheating death. So what does that mean? And the cornerstone of our measure is what we're calling the expected age at death, or the average age reached by individuals of a given birth cohort, provided that they have survived to a given age A, which is a little bit similar to what was already brought in the literature by Vladimir Kanadas-Romo and Elman, which is called the total expected longevity. So basically what we're calling here the expected age at death is the remaining life expectancy at an age A plus the age that you have attained. And we can, because we know that there is a definition that has been established that the remaining life expectancy at age A can be described in terms of the survival, then we can also express this expected age of death in terms of the survival, the life table survival, and here we're going to use the word cohort data plus the age that has been attained. So this is what we're calling this perspective of cheating death. And then it will become clear that then when we say beating the odds, it means when an individual has cheated death sufficient times in order to surpass the expected age that is expected from their average cohort. So beating the odds is at the population level, cheating death is at the individual level. And this is making the translation between these two perspectives. And then in order to do this, what we were thinking is that a way to conceptualize this is that if we have a target age, given an arbitrary target age, for example, becoming a centenarian or reaching at the age of 100, we could define the number of times that the function of the expected age at death needs to be successively applied to itself until this value is greater or equal to our target age, for example, 100. Or it means that mathematically it's just an iterated function that keeps going on itself recursively until you reach the specific target age. And then we're calling these number of iterations I, the number needed to reach the target age. So for example, if you're iterating this function many times, so n times, then this is the number of times one has beaten the odds of dying. Or alternatively, we're also calling this the number of lives lived, like our cat cream puff. So it means that if we keep applying the same function, which are defined as expected age at death, which is basically the remaining life expectancy at specific age, plus the age that you attain, I will show this on the Lexis, become clearer, then this is the number of iterations or the number of times that one has cheated a death. So then this becomes a problem where we need to find an age at which the target age is consistently achieved at by the expected age at death reaching that target age. So one way to show this graphically, this is the pathway of the effort required, for example, to become a centenarian, according to this French cohort of women born in 1875. So just a bit of the spoiler alert, in this cohort of birth, in order to reach the target age of 100, the number of times one needed to beat the odds of dying was 7.95. So a little bit of the cat's version, depending on your culture. And here, this is a little bit of a stylized Lexis because there's, it's a bit of a different way of looking into symmetry. But if we consider what we're talking about beating the odds of dying, is consider this individual who was born in the French cohort of Jeanne Calment in 1875. And according to their life table, their cohort life table, the life expectancy at birth is 48.59. What we're calling that you're beating that, the chances, the odds of dying of the average mortality of this cohort once, means that once you reach the age which was assigned to you at birth of 48, if you reach that age, then you're given another, so to speak, lease on life. Because it was expected by your average that you should be dead by now, but you're not. This is what we're calling a little bit the cheating, because it's the number of draws or the number of individuals that eventually surpass the average, because we know that what we're estimating is always an average. So then if you're beat once, we're still here in the life table world where if you do this, then you're given the remaining life expectancy that this cohort shows that you would have, given that you have lived until 48. So the remaining life expectancy, for example, 48 is 26.22. So then instead of leaving the population or leaving the life table, we bring you back. From the dead. So essentially, for those, we're thinking about this individual that should have died, but that it doesn't because any different reasons. Then you come back with a remaining life expectancy now of the age with which you have achieved, 48.59, plus the remaining life expectancy at that age is 26.22. And then you were granted a new lease on life, and instead of living to 48-ish, now you go to 74.81. And then we're calling beating twice the fact that you've achieved this age. And then again, you're granted a second chance, so to speak. The second chance gives you an extra 8.61 years because you've reached age 75. And this is what the life table assigned to your birth cohort says you could get. Yeah. And then 3 times, for example, then again, for the 3rd time, you're given another chance because you're supposed to die a 2nd time, doesn't work, you're resuscitated, you go back to the population, and then you're granted an extra 5.33 years. And this process can go on indefinitely. And here what we're saying is how many times this process needs to go on in order for you to reach a target age, any target age. And in our case, we're here doing the centenarian, so reaching 100. So the pathway, in a way, the effort that it requires. So how many times do you need to beat the odds of dying of the average mortality of your birth cohort in order to reach 100, given that, of course, the chances to become a centenarian for a birth cohort in 1875, in which lower than the ones born in 2000. So this is a little bit what we're trying to, what we're defining as beating the odds. And then this brings us to some relationships. So for instance, let me do this. So we can define the relationship between the probability to reach this target age and the probability to reach each successive new life. Meaning, what are the odds that you can actually do that? What are the odds that you're beating once, or beating twice, or beating 3 times? And how does that probability relate to the survival? So we have established this relationship. And it means that you can have the series of I iterations, because remember, this is a function, it's just iterated on itself in order to reach any target age. And then we can define this iteration process, both in terms of the expected age at death, and this notation that we're using here, weird notation, it's for composite function in mathematics. So if you're composing a function successively on itself, we can express it both as expected age at death, or we can also express in terms of the iteration I instead of the age A. And this is crucial for us because it will show that we don't depend on the age itself to establish the relationship between these probabilities. So in terms of the iteration I instead of age A, we can also define the relationship like this. That, for instance, the consecutive Li values of the iterations are the probabilities to reach the ith iteration condition, of course, on having survived 2 animals. I can also explain if anyone has doubts on this later, but it's just show how we've come from this crazy idea to the math. So, and then we can, of course, then play around with other relationships that have been established in demography. So we know the lifetime of survival at a given age as a function of the force of mortality, because we are here just thinking in terms of the expected age of death and survival. If we write this in terms of the force of mortality, then we can also show that the probability to outlive one's expected age of death at this nth time of the iteration depends, of course, on having outlived the expected age of death at n-1. When we write this in terms of the force of mortality, these are just details, but this gives us the possibility to prove that the number of these iterations, somehow they converge to a very specific number. And this number is e to the -1. Can go through the proof a little bit more, but I think no one is sometimes interested on this. But the key thing about this is, of course, we're doing some assumptions, is that I'm just going to show this, that the number, so the probability that one beats these odds of dying successively converges to a specific number. And this value has been found in other areas of knowledge that are concerned with the time until failure, time until death. And then from that, we can derive a corollary. And this is important because then we can capture the shift that's generated on this probability by the progressive convergence. So the thing is, when I meaning the number of iterations in our case, meaning the number of times one has beaten the odds, when this number converges, so when it tends to infinity, so we can do this infinitely, right? When this process converges, so the limit of I to the infinity, then the probability converges to e to the -1. But the thing is, when you talk about infinity, then someone will ask, well, don't you have a target age? It doesn't really matter. Someone asked me, well, no one is immortal. No one can beat this indefinitely in real life. But the interesting thing is that this convergence happens quite quickly. So it's not like we're talking about immortality. It's just really talking about the probability to successively reach the beat odds of dying converges to this value, and it converges quite quickly. So here are some applications to make it clear what we're meaning. So here we have different mortality schedules. These are cohorts, so real cohorts from the human mortality database. And then here what we have, sorry, it's not showing, it's I, it's the number of iterations. This I, the iterations are remembering the number of times one has successfully beaten the odds of dying from their cohort. And remember that see that for the French cohort of Jeanne Calment, this was around 8 times, right? And to reach 100. So what we're showing here in this straight line is the value that we found with our proof that in when I tends to infinity, the value that it converges to. And then what we see is quite interesting that, first of all, irrespective of the historical data, this value converges, and it converges quite quickly. What I'm saying quite quickly is with the number, it doesn't go until like 20 or 30. It could go theoretically, yeah, but it just converges to this value. Instead of converging in 20, it converges already, it starts converging in the 6th or 7th time. And this is the probability that you will beat the odds. So it starts, for example, at around 50% for some historical regimes, and then it just falls monotonically, which also for us it's interesting mathematically. And this is for France and Sweden. So we can see that there's almost an overlap. We do have some like variations at the higher orders of iteration. And this we already showed, we tested, it's connected to small numbers of individuals here. And here it's a little bit connected to the strong infant mortality effect. And the way we could see that this is the issue, and it's not our math that's wrong, is that we then simulated different schedules. So this is the historical data, and then we can see below the curves are the simulated schedules. And then we simulated different life expectancies at birth using different converge models. So meaning we're here simulating very different baseline mortality and different rates of aging in order to see how much these curves would also actually converge to this value and resemble historical mortality. And we can see, because these are simulated values, even though we have different shapes here, these are converge schedules. So you see that they're very small and they're very similar. And then this is still not capturing what we see here. And then when we added different simulated values using Mayhem and Seiler models, which can account for strong infant mortality, which are these two here. So we see now that's really what's driving this change. Like doesn't start and just goes monotonically decreasing. It's because of the strong infant mortality effect of this historical cohorts. And then this is the cumulative probability. So here we're showing the trajectory for different mortality schedules of the convergence to e to the -1 of the probability of beating the odds. And here we show the cumulative probability to successively outlive one expected age of death. And again, in a set of the historical, which are these ones, the same we showed before, and the theoretical mortality schedules, which include converts, and also silent and Mayhem, so we could simulate the infant mortality. And what's shown here, just to understand a little bit, again, we have the iterations at the x-axis, and the y-axis, the logarithm of this probability to accumulate it, right? And then here we have the value of e to the -1. And then we see that most of this probability, so when you accumulate them, they fall, all of them fall, most of the times, except with the beginning of which is probably related to what we're discussing before, they all fall again between two values of either 1.5 minus I, the number of iterations, or 1 minus I. So it's really interesting because you were showing that all of these historical sets of values and simulated values, they converge to one number. And they are related by a very specific relationship, regardless of the trajectory, the mortality trajectory. So this will become clearer now. So this is a consequence. So it means that the number of lives needed to reach this target age, which is arbitrarily given, in our case, we're giving the examples of 100, they can be expressed as a simple logarithm transform of the probability to reach that age. So this is what's been shown here. So, and this value for most historical, like think about the broadness of mortality experience in the history of humankind, we can approximate this by this equation. And since this value itself is not a function of age, but only of the probability that you survive to that age, then the number of lives lived, as we're calling it, can be computed from the probability itself. So for instance, we can make statements such as when an individual survives to an age that is reached only by 1% of the members of their birth cohort, so regardless of what that age is. So the individual survives to an age that only 1% is the definition, is reached by the members of the birth cohort. This means that they have cheated death about, and then we can use this definition, around 6 times. So we can reach this value of how many times one has cheated death, or how many lives lived, or how many like cream puffs possibility by this single relationship. So this means that this result is independent from that target age, and that corresponds to the survival level. And this is important because it shows that this is somehow a relative measure of time. And it's a measure that's connected not to the age itself, but to the specific population to which the individual belongs. So it was signed slightly differently. We can see that this probability is incredibly stable across different mortality contexts, and this makes lives lived in a way a universal sort of measure of time that is comparable across extremely diverse populations. There has been some interesting results connected to this. I mean, trying to go a little bit beyond age, so to speak, in a very, very beautiful paper by Jim Vaupel, that they also use what they're called S ages. So they're really like measuring, they're not looking at like only mortality rates at the age fixed, but the levels of survival that the groups of individuals have achieved. And just to show you a little bit before I finish, that I'm going to switch to my other presentation because I want to just show a little bit for your patience. Because one of the things that we were thinking so much about this is that it's so to go a little bit beyond, yeah. So like I mentioned before, this is a measure based on a definition of time that becomes a little bit independent from the necessarily arbitrary measures of time that are used to compute the risk of death. Of course, ours also has a level of degree of arbitrariness like any measure, but we're trying to go a little bit beyond age. And we see some of the advantages, for example, of doing this approach, because one may ask, why are you trying to compare us to cream puff and how much is that useful? So in a way, it is likely that, for example, this probability or the effort it takes to reach this target age, for example, to become a centenarian, is more strongly correlated, for instance, to remaining life expectancy at age 60 than to life expectancy at birth, which is sometimes the measure that is used to discuss longevity. But contrary to remaining life expectancy at age 60, which is already a conditioned measure of survival, when we're looking at N100, so this probability that we're proposing, it includes the mortality experiences of all ages. So it is not conditioned to having survived to any given age, because it gives all of the effort that is taken ever since you were born. And contrary to life expectancy at birth, it is not heavily dependent on infant mortality, which we saw, of course, impacts a lot the measures of life expectancy at birth. It has also been shown by some studies in biology that the average maximum age is reached by about 1 to 5% of individuals in a cohort. So it's quite interesting. It seems that even for other species, when we try to go detach a little bit beyond age, we can see that regardless of that age, the maximum age possible is usually quite constant in history and quite constant across species, meaning it's usually around 1 to 5% of individuals that will get to be lucky enough to, consistently cheat death, so to speak. And it has been shown in these papers that the mortality follows this exponential decay, which is similar to what we saw with this converges to the -1. And it would mean that if this relationship is also holding for different species, that we could have a little bit like a, how can I say, it's a bit ambitious, but a general way of defining mortality. And then just to be a bit provocative with this, we're thinking how much our chronological ages are anchored in demography, but also our curves. in a way that it's very difficult to go beyond this. And I think it's really interesting, some movements that are happening in fields outside of our area. So for instance, in marketing, people are already discussing the ageless consumer, the fact that defining senior categories are very arbitrary. And of course, we have like huge efforts to try and correct for that. So we know the expected age from Wars and Charbol, but they are all indicators that are trying to keep, they're still attached to age and they're correcting for characteristics. But in a way, we're always going to have to keep correcting, right? But what if there was a way to go a little bit beyond that? And just to give a little bit to left remarks, is that South Koreans, for example, don't have only one age, right? You have different definitions of age. You have now the international age, which was created because there's a handbook. You have the Korean age, you have the calendar age. So it just to remind us of how age is an arbitrary measure, and of course important, not to just we take age out of the equation, but just how can we think about pushing the boundaries of the discipline and trying to go a little bit, thinking a little bit beyond age. And this is because, of course, there has been a changing relationship between age, survival, and life cycles, and this is demanding somehow a little bit of review of that. And we expect this work to be some sort of a stepping stone in that direction. Thank you. Sorry for the confusion with the